Hello. It's Thursday, the 14th of November. This is a review video for Healey Chapters 5 through 9. That's 5 chapters. Review for the exam 3 on those 5 chapters. Let me tell you a little bit about why we're doing 5 through 9 as a cluster, and I'll tell you a little bit about the exam, and then I'll walk you through the review. Chapter 6 begins inferential statistics, and as you know, with the diagram I put up on the board before, population to parameter, drawing down a sample, going over the statistic to estimate the parameter, that we've really been talking about inferential statistics from day one, whether it is a rate or a ratio or cross tabulation, which is homework next week. Any of the statistics that we've done in this semester are really about inferential. They're all happening at the statistics level from the sample, and they're used to estimate what we would have found had we gone from population to parameter. But we can say with Chapter 6 we're more formally into inferential statistics. And I've included Chapter 5 because so much of the way we express inferential statistics is with normal curves. You'll remember from Chapter 6 that there are 3 levels of normal curves. There is the empirical one of the sample, and then there's the one that we expect is up there from the population, and then there's the hypothetical one, the sampling distribution, which we'll talk about here again in a minute. But in order to understand the dynamics of the normalcy of these distributions, it's good to look at Chapter 5 because that's where the normal curve is introduced. And it is a foundational concept in inferential statistics. So we're beginning with Chapter 5. And then 6 is the theoretical piece, I suppose you'd say. And then 7 is the confidence intervals, and then 8 or 9 are some examples of one case and 2 case applications of that. But we'll talk about that here in a few minutes. The exam is 50 multiple choice questions. I'd show it to you, but you could expand up you probably would too. Expand up the picture and look at it. No, I'll show it to you. I meant to pull it out. It's I don't see. Here it is. No, that isn't it. But anyway, it is 50 questions, and those of you that are online, this video sometimes I will hand over to the email to the face-to-face class. But it's really directed to the online 3311. You'll do this on Blackboard, and the 50 questions will be posted up there like they were for Exam 2, and then you'll take it, and it'll take a week. Give you a week once we start. And I'll send you an email about when we start. I haven't put the exam up on Blackboard yet. I'm not sure I'm going to be able to do that today. So it'll probably be tomorrow, and it could be as late as Monday. So we may be doing Exam 3 for the online course all of next week. The face-to-face is starting this afternoon and goes on through Saturday. But anyway, 50 multiple choice questions, 10 multiple choice questions for each of the 5 chapters, and it's 2 points each, and the usual range, 90 to 100 is an A, and 80 to 89 is a B, and that sort of thing. And there'll be some of that description on the exam itself, on the electronic version of it on Blackboard, about what the expectations are and how the grades will be distributed. But you won't see your grade until the whole thing is finished. If I post it until midnight on Friday of this next week, grades won't appear to you until after midnight on Friday of this next week. And likely, like what I did before, and I did with the face-to-face, I'll look at the maximum score of 100 and look at the highest score and give some consideration to curving. Multiple choice questions seem to be easy when you think about it, but when you get down to it and you see 4 choices and they all seem so familiar, and I can tell you that this exam is going to be more conceptual than mathematical and for calculations. So very much more conceptual than the one in the past, 2. So let me say, having said that, one way to approach these 5 chapters is pay close attention to everything in the chapters, all 5 chapters, that have terms that are bolded. Like if we look at Chapter 5 here, for example, the very first page, there's 2 bolded words, normal curve. You want to know how, if there's 4 options to define that, which option is the correct one. So as you work your way through these 5 chapters, pay special attention to the bolded terms. You can have all the reason in the world to expect that those bolded terms, or at least most of them, will be on the exam in one form or another. Those are the conceptual pieces. The formulas and the calculations are of course, more mathematical. But as we said in the syllabus in the beginning, it's far more important to me that you have a conceptual understanding, a critical thinking understanding of statistics than the actual math calculations of statistics. That's what homework's about. Exams are about exploring, giving you an opportunity to explore the more conceptual side of it. Okay, having said that, let's talk about Chapter 5 for a minute. We know about normalcy. We know that a normal curve is symmetrical. We know from previous times a curve that's not symmetrical is called skewed because it's got a tail off to the right or a tail off to the left. So know that it's symmetrical, and that's how we define normalcy. So keep those kinds of things in mind as you work your way through this stuff for Chapter 5. I point out here figure 5.3. It's on page 117 of the text. A lot of the questions in Chapter 5 are around the theme of this figure. These are the 3 standard deviations on either side of the mean. And as that figure points out, 68% of any continuous distribution lies between 1 plus 1 or minus 1 standard deviations around the mean. 95% is plus or minus 2 standard deviations. 99% of any continuous distribution is between plus or minus 3 standard deviations. So be familiar with this. Know 68, know 95, know 99, know the normalcy, know all that kind of stuff. And also be able to remember that we may say this is the proportion is 68, but if we were multiplying it times 100, then 68% lie between here, these 2 standard deviations. If we were to think of probability, then we would say 68 out of 100 lie between these 2 standard deviations. So when we look at this figure, think of it in terms of proportions, 0.68. Think of it in terms of percentages, multiplying it times 100. Think of it in terms as expressed as a probability, 95 out of 100 lie between these plus or minus 2 standard deviations. And also be able to think as if the question were to ask you, what's the probability of some particular amount of distribution occurring? What's the probability of it occurring between the mean, which is here, between the mean and the first standard deviation? What's the probability of that occurring between the mean and the first standard deviation? Well, what you would do with that is you take 68. This is not working here. You take 60. Oops, that one's not working either. Well, let's try this one. You take 68 and divide that by 2, and you get 34. So 34% of the distribution lies between the mean and the first standard deviation, and same on the lower side too. So then, if the probability is, then it'd be 34 out of 100 of that distribution is going to happen between the mean and the first standard deviation above the mean or below the mean. So be able to work your way through this particular figure. A lot of the questions on the exam are around concepts related to this figure. So study it, figure it out, think about the proportions and probabilities, and you should be in pretty good shape. The other thing to keep in mind is that z-scores, pardon my back, z equals standard deviation. Now, these are kind of the standardized deviations, the 3 that are above and below. But every time we plot out a turtle, shall we say, a z-score, let's say that we've got a z-score of 1.5, then that's a plus. So here's 1, so it would lie about right here. And so we would draw a line that represents that z-score, and we look at how much of the distribution is above it and how much of the distribution is below it. So that 1.5 is actually a standard deviation. So every z-score equals a standard deviation, a unique one. Not the standard deviations, but a standard deviation nonetheless. So keep that concept in mind as well. and then be able to calculate out, and I'll refer you here, I'm flipping over to a table, table 5.3 on page 125. Be able to understand and identify the correct answer if they were to ask you, how would you sum up the amount of the distribution between two z-scores, one on one side of the mean and one on the other? How would you sum up the distribution that lies between those two z-scores? Or if the question is, if you've got a z-score on both two z-scores on the same side of the mean, then how would you derive the amount of the distribution, or proportion of the distribution, or percentage of the distribution, or the probability distribution that lies between those two z-scores on either side of the mean? Not one on either side, not one on one side, one on the other, but both z-scores on the same side. Take a look at table 5.3, and that will help refresh your memory on this. And there are plenty of illustrations in Healey on how to do that, that you can practice. The last thing to keep in mind is what I was saying at the beginning. Anytime we're talking about this, we start off with proportions and multiply them times 100, and that's a percentage. But the other way of thinking about this is probability. What is the probability of something lying here? Or what's the probability of something here? Or what's the probability between two standard deviations of plus or two out of 100? Two standard deviations plus or minus standard deviations around the mean. If I'm saying that clearly, that would be 95 out of 100. Be able to express the probability statements related to this. Anything that's below the mean, 50 out of 100 lie below the mean. 50 out of 100 lie above the mean because it's symmetrical. 95 out of 100 lie between the two standard deviations. 99 out of 100, that's a probability statement, lie within the three standard deviations plus or minus the mean. So be sure and be able to do that. And then let's go on to chapter 6. This is where we formally get into inferential statistics. And pardon my back for a second. I want to erase this so I can highlight a couple of things here. One of the things, let me take a moment here and put this up here. I'm going to put up things that we've done before. Population, the parameter, down to the sample, and across to the statistic, and then up to the parameter. This pathway expresses inferential statistic. We can't go this way to get the parameter. That's what we want, but it's too expensive trying to ask a million people. We draw down a sample, and we get a statistic, and with the statistic, we estimate the parameter. Now, one of the things that's going to be you need to keep in mind, a population is a population. The parameter is related to the population. This is what we're after. But we draw down a sample. The statistic is related to the sample. So another way of saying it, the statistic is to the sample what the parameter is to the population. You want to keep that in mind, and maybe keep this pathway image in mind. Maybe it'll be useful for you to make that distinction. So the difference between population and parameter, and sample and population and parameter and statistic is important. Now, if we do random, chapter 6 talks about sampling, or I should say ways of doing samples. Random samples. We can do a simple random sample, that's one of them, clustered random clustered sample, or random kind of systematic sample, or a stratified sample. Be mindful of the 4 kinds of sample types that are in chapter 6. I'm sure you'll be asked to distinguish one from the other in some form on that exam. If these are random from the population, then they are unbiased. In other words, they are representative. I was using this morning in class. If I were to select a sample from the population of old white boys like me, then that would be a bias. It would not be representative because the population is not filled of old white boys like me. So if I do it randomly, I'm going to get a good mix of the demographics of the population. There might be 1 or 2 old white boys in there, but it'll be the demographics of the population will be represented in the sample. So that when I'm talking to the sample, let's say we're doing a survey, we're in a sense talking to the population. So a random sample is going to give us some assurance of getting representation there. And it would be unbiased. The other thing in here is that we want to think about is in Chapter 6 is the central limit theorem. The central limit theorem in Chapter 6 tells us, as we know, the larger the sample size, the more efficient, this is a term from Chapter 7 actually, the larger the sample size, the more efficient is the estimate, the more precise is the estimate of that. And we've demonstrated that to ourselves before. The larger the sample, the more heaped is the normal curve. More heaped is the normal curve, the better the estimate of that curve is of what we expect that heaped curve is up in the population distribution. So in Chapter 7, we're reaching ahead a little bit here, biased is, you avoid a bias by a random sample. You get something that's representative. These are contrary to one another. If it's representative, it's not biased. The larger your sample size, the more efficient is the estimate. And this piece right here, that's the inference. Here we're making the inference that had we gone this way, we would have found basically what we found going this way. So that's inferential statistics, walking this kind of, if you will, circumlocuted or circumambulated or convoluted, if you like, pathway in order to get the answer that we wanted if we could have gone this straight across on this pathway here. So keeps those types of samples. And then the other thing that you want to keep in mind, I'm going to do a drawing over here, is that we've got 3 normal curves. These are not, they don't look so normal, but that's what I intend them to be. I'm not an artist. This sample curve here, this curve is your sample, the distribution of your sample. This is the sampling distribution, and this is the population distribution. Now this one is empirical. We can do it right out of the statistics, what we get from our survey or whatever. And if we've got something, central limit theorem says that if you've got an n or a sample greater than or equal to 100, it's going to take a normal distribution. So here we've got a normal distribution empirically. We assume this is normal because it's like 1 million people up here, so this is probably normal. It's probably pretty heaped, probably a pretty heaped thing. This one, the sampling distribution, this one is a special one. Here, reaching again in Chapter 7, this is our, I'm going to write it here, a point estimate. We draw that sample down and we're taking care that it's unbiased, it's sufficient size so it's efficient, but it's a single point estimate of what's up in the population of the parameter. Just a single point. We know, do we not, now that we are statisticians, are we not, that if we were to do 100 samples of the same size, call it 1,000 each sample, if we did 100 samples of the same size, and we were talking about average age, because each of those samples of 1,000 would have 1,000 different people in it, there'd be some variability in the average age. So we know there's going to be a little range from, say, the mean low to the mean high. And so then we say, if we were to do 100 samples of the same size, here we've got the mean low and the mean high in the sampling distribution, where this has standard deviations, which will not be on the exam. This one has standard errors, which might be on the exam, but I don't think so. I don't recall having put that on the exam, because it's not so important at this point. That this is a distribution of 100 hypothetical samples, which, because it's over 100, simple limit theorem, it's going to take normalcy. And then this, the theorem, if you read it, the mean, the middle mean, the big mean of the means here, is considered to be a more accurate, or the most accurate estimate of what that population mean, which we denote as a mu. So this then, we can say, if we were to do 100 samples of the same size, this is the kind of distribution we would get. And leading into the Chapter 7, if we were to go back to where we've got, I think that's about right, 95%, then 95 out of 100, when we talk about confidence intervals, why we like this particular image is here, this is a point estimate, but if we can say 100 out of 100 samples, 95 out of 100 will range between this mean here and this mean here, then it's like casting a net into the waters, and we can say that somewhere in this net is the true mean. We think it's this because we've been efficient and we're unbiased. We have a sample size, a good size sample, and it's random, a random sample. We believe that this is it and that this is it, but we recognize there's some variability, but we don't think, the chances are 95 out of 100, the true mean lies somewhere in there. So that's what the Chapter 7 confidence interval is about. We'll come back to that in a second. The important thing is that the population distribution, the sampling distribution, and the distribution of the sample. Be able to recognize that there are three distributions. One's empirical, one is supposed to be out there, we suppose it to be, and then this one is a hypothetical, and that sort of thing. And be mindful of the theorems in Chapter 6. The principal one is central limit theorem. The larger the sample size, the more efficient, the closer we get to the true parameter. And the other theorem talks about how this is going to be likely to be the true value. This and this are likely to be equal. Okay, that's Chapter 6. Let's look at Chapter 7. Let me erase some of this. Chapter 7 is the confidence interval. And here we're back to the idea, like we were just talking about a minute ago, what's coming down from the sample is a point estimate. And we know there's variability if we were to do 100 samples, because we're not asking the same 1,000 people 100 times what their age is. We're asking 100 times, each time 1,000 different people. So we can expect variability. So when we get this curve out here, this is the sampling this is the distribution of the sample that we just saw in Chapter 6. We bring that forward, and here would be our mean, let's say, and then we use, for the most part, in statistics, we use the 95% probability. So the mean in that distribution here and here, now there are going to be means out here, not so many, 5 actually, maybe 2.5, 2 over here and 2 over there. But we're saying 95 out of 100 of those means, in other words, 95 out of 100, they're going to be, chances are they're going to be between these two means here, which give us a little extra confidence or assurance that we're capturing the true parameter that we were talking about a few minutes ago in that diagram. So we do the confidence interval realizing that there's variability in point estimates if we were to do 100 of the same size sample. And there again, if they open that chapter with bias and efficiency. If we are random, then we're non-biased, we're representative. And if we've got a central limit theorem, a large enough sample, then we're going to be more efficient in our estimates. Now the other thing that's important to think about here is the width of the interval. The basic principle here is sample size, and you'll see that in section 7.7 of that chapter. It's basically the larger the sample size, you can see a good illustration of that, I think, would be if I just pointed it out rather than drawing it.